Early Experimental Psychology, Part 1, Vitalism through Müller. History and Systems of Psychology, Department of Psychology, California State University, Fresno, Professor Michael Botwin. Welcome back to the History of Psychology. I'm Dr. Mike Botwin. Now, in our opening slide, you saw a picture of the Sistine Chapel by Michelangelo. And it is a famous painting of God, always interpreted as giving the spark of life to Adam. Well, I want to turn that upside down for you a little bit, or at least give you something to think about with it as we embark on studying how folks historically studied the brain. To be a little redundant, this picture is kind of like a chicken and egg question. Which came first? And I'm going to put the context there. Well, I'll answer that question because I know what came first, the chicken or the egg. It actually was the egg, as chickens have evolved from dinosaurs, and dinosaurs laid eggs. So I've answered that major question for you in today's video lecture. But let's look at Michelangelo's paradox. Several years ago, some researchers published an intriguing article where they speculated that the image of God on the Sistine Chapel ceiling was actually surrounded not by a cape, but that was actually a brain case. And if you look carefully at the image here, around the red lines, you see it kind of looks like a brain case, with the brain being inside of it, and there being the convolutions of the brain formed by the cherubic angels surrounding God. God's legs kind of go off making a brainstem. It's a very intriguing notion. Let's look at this in a little bit more detail. Here is an image of the brain that I've made kind of transparent. To be really honest, when I first did this exercise, even though I've been lecturing on the Michelangelo God brain for quite a while, I was shocked when I superimposed this brain over the picture of God. So let me show you how this works. Here we have our picture. Here we have the brain you just saw in the previous slide, superimposed transparently over the Sistine Chapel painting. I was amazed at how remarkable the fit was. I thought I was going to have to play and pull around with the picture a bit. Didn't have to, just had to change it to make it the same size. People have speculated as to the meaning of this. One interpretation is that God is imbuing great intellect to Adam by bringing the brain to him. But there's even a little bit more of a radical and subversive interpretation of this picture. Let me show you. So here's the paradox. Is God creating Adam in his image? Or is Adam creating God in his brain? So what came first, God or Adam or God? That's a chicken and egg question I won't be able to answer for you today. You'll have to figure that one out for yourself. In the meantime, let's get on to science and brain stuff. Frederick Bessel is important for being one of the first scientists to note individual differences in human performance. Did it in an interesting way. He heard about this story that is very important to the world of 18th and 19th century astronomy. There are two astronomers, a senior and junior one. The junior had just been hired. The junior astronomer would make an observation. It would always be slightly slower than the observation of the senior astronomer. Now, modern computer technology has made this obsolete, but at Bessel's time, the astronomers would look through their telescope and then record movements of stars with their stopwatches and then write down their observations. Now, what happened is the junior astronomer was always slightly slower than the senior one. And the senior one sat down and talked to the junior one and said, you have to get your act together. You're slower than me. You're going to have to get your observations on time. It never worked out, and unfortunately for the junior astronomer, he was let go. Bessel started looking at the differences in observations of astronomers and found that all the astronomers were making different observations. Now, the differences were very, very slight, but they were primarily due to the reaction time between making the observation, seeing something in the telescope, and the time it took to press the button on the stopwatch. Some astronomers had quicker reaction times than others who were a little bit more slow. None of them were necessarily bad astronomers. They just had these differences in reaction time. To correct for this, Bessel creates the personal equation. It's kind of similar to a golf handicap. It makes everyone equal. Bessel recorded an equation for each astronomer. Eventually, in astronomy, each astronomer had their own personal equation that factored in their reaction times so that all observations ended up equal. As a personality guy who's very interested in how we systematically differ, this is something that really fascinates me. In 1818, Mary Shelley published the book Frankenstein. It started out as a short story she wrote with a group of other literary English types while visiting Switzerland. Each was given the task of writing a horror story. The other story that came out of it is another one you'd know, Bram Stoker's Dracula. But Frankenstein's the order of the day here. Now, Mary Shelley wrote this book reacting to something going on in the zeitgeist of the day. And it's basically the idea of electricity and electricity in the body. Now, this gets us back to our old vitalism versus anti-vitalism debate. The notion that either there is a spark of life, a soul that we have in our body that is an integral part of our being, versus the anti-vitalist movement, which says we're just a sum of our biochemical electrical reactions. This is essentially the philosophical notion behind Frankenstein. Can you take a dead body, if the only thing missing is electricity, and reanimate that body by pumping in some new electricity? Well, you may have seen the old horror story versions of Frankenstein in one way or another, or my favorite version of Frankenstein, the Mel Brooks Young Frankenstein. But the basics are there in any of the versions of that story. You collect a dead body. You expose it to great amounts of electricity. Does that body return to life? Well, in reality, we know the answer is no. Modern medicine has provided us with electrical paddles to restart a heart that's undergone cardiac arrest. Now, it won't work on a body several days old, but it'll jumpstart a person and get them going again. So, little grain of truth in the Frankenstein story. Frankenstein was 19th century science fiction. Scientists were just starting to find out what electricity could and could not do, and were trying to harness it. This is the whole science fiction behind Frankenstein. Now, instead of electricity in our science fiction stories, we now talk about DNA experiments gone bad, cloning experiments gone bad, things like that. But at the time, electricity was a brand new thing. People were scared to have electricity in their house. Here's another still from Young Frankenstein with Peter Boyle playing the monster. But people were scared to have electricity in their homes. They were worried about electricity leaking out of outlets. There was much contention when we get to the early 20th century as to which form of electricity should be used publicly. And the primary debate was between Tesla's form of electricity and Thomas Edison's form of electricity. In an early propaganda movie, one of the first movies ever made, Edison electrocutes an elephant using Tesla's system of electricity to show how dangerous it is. Now, we don't think twice about electricity in our houses. In fact, if the electricity goes out, it's a major inconvenience. But we have to remember it's a new technology that's really only been around in households for a little over 100 years. So electricity in the body starts to become a major scientific area of investigation. Charles Bell is the first of our scientists to make important discoveries about the nervous system. And he, along with Francois Magendie, who independently made this discovery in France, differentiated between sensory and motor neurons. Hence, finding there are two distinct kinds of neurons. They demonstrated that the posterior root of the neuron elicited pain, while stimulation of the anterior root of the neuron produced motor effects. Hence, you get what becomes known as the Bell-Magendie law, where you have neurons that are specialized for either sensory or motor functions. Now, the Bell-Magendie law has two important corollaries. First, the notion that some neurons are specialized. They're either sensory neurons or motor neurons. And secondly, their major discovery was that neural conduction occurs in only one direction. Neurons don't conduct impulses in two directions. They only go one way. This was the first major finding about neural processing systems in our body. Our next individual is Johannes Müller. And Müller made many different contributions to physiology in the 19th century. He also speculated as to the nature of the nervous system in a couple of important ways. First, he said it's the central nervous system, not the stimulus, that determines our reaction to stimuli. So he's kind of taking the approach that if you sense something, what you're receiving in the brain are signals about that stimuli, nothing about the stimuli in and of itself. He also says the nervous system serves as an intermediary between sensed objects and the mind. And as you remember from our previous sections on rationalism and empiricism, you can see this is an extremely important finding. He takes Bell and Magendie's work in sensory and motor neurons and expands it into what he calls the doctrine of specific nerve energies. According to Müller, the central nervous system controls sensations moving from the senses to the brain. That was already established by Bell and Magendie, but the doctrine of specific nerve energies goes one step further and says the neurons associated with each of the five senses have their own specific type of energy. He went so far as to say that if you were to wire up an eye with the nerves from the auditory canal, you would hear sights and things you would visually process. Kind of interesting and wild speculation there. Now, he also accounted for motor movement by saying there was muscle sense, and each motor neuron also had their specific nerve energy. So he comes up with 6 specific nerve energies. He attributed the quality of an experience to the specific quality of the energy of the nerves. So here is, again, the example I just gave you. If you were to take the neurons involved in audition, wire them up to the eye, you would hear sights. And vice versa, if you took the optic nerves, wired them to the ear, you'd see sounds. He also talks about each type of specific nerve energy having an adequate level of stimulation that's specific to each of the senses. So the easiest example to explain that is vision. Most of the time when we see something, we're bringing in visual information through our eyes into the optic nerves, processing to the occipital lobe. However, if we were to press hard against our eye, we would, through that pressure, get a different kind of visual stimulus. But it's not the adequate one that properly energizes those nerves. Müller says we're conscious of sensations, not of physical reality. Kind of sounds like our old friend Berkeley, doesn't it? So according to Müller, we're only aware of sensory impulses, not of the objects themselves. And that would be a fairly modern view of how sensation works. We'll expand on this early psychophysiology in the next lecture in the history of psychology. This has been a We Have Couches video production. Copyright 2020, Professor Michael Bontwin. All rights reserved. Bye now.